Okay, continuing with linear programming today, let's take a look at a couple of examples in 2.3. So nothing new from 2.2. These problems tend to be minimization instead of maximization, but the basic mathematical concept will be the same. So we have a problem. Minimum daily requirements from a powdered dietary supplement are 1,200 units of vitamin A, units of B, units of C. An ounce of dietary powder X costs $3, Y costs $2. I keep reading, and then I see a question that says, how many ounces? So if I look at that question, how many ounces of each powder should be consumed each day to minimize cost and meet the daily requirements? So when I look at that question, that indicates to me the variables are the powder X and the powder Y. So I'm just going to use X equal, that's going to be the amount of ounces of powder X, and Y is going to be equal to the ounces of powder Y. And then I see several constraints around vitamin A, vitamin C. Then it looks at, okay, what am I asked to optimize? So I'm looking for minimizing cost. Okay, so what I'm looking for is the cost, and I'm being asked to minimize that cost. Now, where would I get the cost from? If I look closely at the problem, it tells me that X costs $3 and Y costs $2. So my cost is going to be X costs $3 and Y costs $2. So just double check everything. That was $3 for X and $2 for Y. And I'm good to go there. Now, let's look at the constraints that I have. So if I look at my constraints here, I've got powder X, I've got powder Y, and then I have 3 vitamins that make up each of those powders. So I've got vitamin A, I've got vitamin B, and vitamin C. And then I know I have certain amounts of each of those. So if I look over the problem and the table, it tells me that powder X has 500 of A. So it has 500 of A. It has 100 of B, and it has 100 of C. And then I see powder Y has 200 of A. It has 200 of B and 400 of C. And then if I look further up in the problem, it tells me that my minimum daily requirements, I must have 1,200 of vitamin A. So if it's a minimum, that means I've got to have, that's the smallest amount can I have. So I've got to have at least 1,200 of vitamin A. I've got to have vitamin B, 800. And then it tells me there's 1,000 for vitamin C. So that's going to tell me what my constraints are. So each of those is going to define for me the constraints that I'll need to map. So let's just sort of rehash what we've written so far. We've got our variables. Remember that X equal the ounces of powder X, Y equal the ounces of powder Y. My objective function was minimizing the cost. Remember, I wanted to minimize the cost, and the cost was 2X plus 3Y. And then if I look at it, I've got constraints here. What's a little bit different is I've got more constraints than what I've dealt with before. So in this case, let's look at different colors for this. We always know that X is greater than or equals 0, Y is greater than or equals 0. And remember, we taught ourselves that whichever variable I list first, that's my horizontal axis. Whichever I list second is my vertical axis. So I've got the constraints, and I'm just going to pull these constraints from the chart you see here. 500x, 200y, those are my constraints that I'm going to need to map. So let's look at each of those. So 500x plus 200y, and we know that that's going to be greater than or equal to 1200. And then what are my other constraints? I've got 100x, so 100x plus 200y is greater than or equal to 800. And then I also have 100x plus 400y greater than or equal to 1000. So now I just need to graph each of these regions. So let's look at x, y. So in this case, if x is equal to 0, I've got 200y equal 1200, so y is equal to 6. If y is equal to 0, then I've got 1200 over 500, that's 12 fifths. So that's going to be 2.4. So remember that's 12 fifths, that's 2 and 2 fifths, 2.4. Now if I look at this one, x and y, when x is equal to 0, 200 times y is 800, that means y is equal to 4. When y is equal to 0, x is equal to 8. And the last one, when x is equal to 0, y is equal to 2.5. And when y is equal to 0, x is equal to 10. Okay, that gives me enough to graph each of these lines. And remember, with these greater thans, I'm shading above every one of these lines for my feasible region. So let's graph these. So 0, 6. So first of all, look, x needs to go from 0 to the largest number I see is 10. So the x-axis has to go from 0 to 10. The y-axis needs to go up to 6. So in that case, I could just take this normal scaling of 1 for every. So 2, 4, 6. Sorry, I can back up, make that a little bit larger. I can do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the same on the vertical axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So to graph 0, 6, so with green, 0, 6 is right here. 2.40 is going to be here. So I need to connect those lines. So okay, and then if I go to the red line, I've got 0, 4, which is right here, and 8, 0 over here. So to connect those, so 0, 4 connected with 8, 0. Okay. And the last one, 0, 2.5. So that is right here, and 10, 0 way over here. So to connect those, okay, each of these inequalities is a greater than inequality. So I'm shading above each of these lines. So my feasible region is all of this, okay? So that means if I try to identify my vertices, this is a vertex, this, and over here. So I have 4 of them. So the first one I know, it's the point right here. That's one vertex, and the other one looks like on the blue line right here. So I know those 0, 6, and 10, 0. Now I just need to find the intersection points. So let me write down the ones that I know. I know I've got 0, 6, so 0, 6, and 10, 0. So what I need to find is the intersection of, it looks like the green line and the red line, and then the intersection of the red line and the blue line. So for the green line and the red line, I can do that with matrices. So I can say that xy is equal to 500, 200, 100, 200, inverse times 200, 800. So that will give me the XY point for the intersection of the red and the green. And if I do that, I think I've already done that on my calculator. So if I look at that, so that tells me 1 7/2. So 1 7/2, that's 1 3.5 would be this point right here. So 1, that's the point 1 and 3.5. Now the intersection of the red line with the blue line, I can do that with matrices as well. I'm going to have xy is equal to 100, 200, 100, 400, inverse of that matrix times the solution 800, 1000. And I've entered that already in my calculator. 100, 200, 100, 400, 800, 1000, and I get 6.1 for the answer there. So that tells me that xy is 6.1. So that tells me this point right here is 6.1. So now I have all of my vertices. So I've got, what were they? 1, 3.5, and 6.1. Now I just go back to my cost function. So my cost function was 3x plus 2y. So the cost at 0, 6 is going to be 3 times 0 plus 2 times 6, which is 12. The cost at 10, 0 is going to be 3 times 10 plus 2 times 0, which is 30. And then the cost at 1, 3.5 is going to be 3 times 1 plus 2 times 3.5, that's 7 plus 3, that's 10. And then the cost at 6.1 is going to be 3 times 6 plus 2 times 1, that's 18 plus 2, that is 20. So it looks like the lowest cost will be right here. So now I see that if I go back to my original question, they were asking me how many should be consumed each day to minimize the cost and still meet the minimum daily requirements. So in order to do that, so I should have, it looks like my answer would be 1 ounce of X and 3.5. So it's 1 ounce of powder X, 3.5 ounce of powder Y to minimize the cost at, and I believe that's going to be $10. Okay, so this one was a little bit longer because it had 3 inequalities. And so when I graphed the region, I got 3 lines, so I could easily find the vertex points that were on the X and Y axis, but I had to look at the intersection of 2 different lines. A great case here for why color is helpful, because I didn't have just 2 lines intersection, I had 3 lines, and I had to know which ones were intersecting to find which points. So anyway, that's the first example of the problem we work in class on section 2.3.